All right, let's look again at some of these other problems and see what else we have. Okay, this is another one that is similar to ones you may find in a regular text. And I'm going to do something kind of ridiculous here. Um, let's go ahead and create another one of these here. Okay, so let's say you had a collar and it basically, so you had some sort of collar that was on here and that was pulled by a rope here, sat in a pulley and was pulled on a force here. So here's your rope. Essentially, the blue line is the rope, now that I've made it sort of red to begin with. This collar is going to just basically follow this path. And as long as it doesn't kink at any point, it may end up, say, directly under it. Now, if you had some of these dimensions, like, for example, let's say this was 5 feet, and let's say this was like 12 feet, and this total distance from here to here was, say, I'm just making stuff up, 20 feet. And let's say this was 100 pounds, then what's the work added to this thing? If you think about it, um, there's no spring, so you could call this state 1 and this state 2. So you would have mg, and whatever this is, that's the mass of it, mg h1 plus, and there is nothing else, there is no, I could do this, but if it starts at rest, that's 0. Then a force dotted with the distance is equal to mg h2 plus 1/2 m v2 squared. Okay, so if I put my datum here, then the height 1 would be 0. Height 2 would be 20 minus 5, or 15. So this would give you 15. This would give you 0. So you'd have 0 plus f dotted with a d is equal to mg times 15 feet, so whatever the weight of this thing is, plus 1/2 m v squared. Here is your key. If you went in and painted a section of rope here, just right here, and you looked at the distance from here to here, okay, let me use this. If you looked at the distance from here to here, it would be the part that is yellow here. That part's easy to figure out. The length of that yellow is equal to, looks to me to be square root of, go from here to here, give me 12, plus from the bottom to the top, it'd give me 20 squared. That'd be the length of the yellow. Let's look at the length of the violet, which is this. Length of the violet, I don't know how to spell violet, but I can look it up, is equal to 5. So it's pretty obvious that the delta, the amount the thing moved was, okay, and I can figure this out here. There, square root of 12 squared plus 20 squared, 23.8 32, 23.32. So that you paint this spot, if you painted it, it would move out here. The delta between these 23 minus 30 or 0.32 minus 5, and that would be the amount it would move. So this workload would be 100 times 23.32 minus 5, and that would be the work added. The reason it's work added is the distance it moved is in the same direction as the force being applied. And then you just work this out. You put in your weight, you put in the mass here, you take the square root, and you're done. So it seems like the drawing is complex there, but it has nothing, it's not that complex. Okay. Okay, I'm not having success moving things around. Okay. And that's a similar situation. It's just trig. I mean, not trig, but taking the, guess you could say it's trig. But it's just finding out the distance that this rope moves. And let's see. At this point, let me go back. Go to the Google Drive. Go back in here when it does come up. Wait. Come on. Okay, here's your take-home test. And let's look at these three. I mean, I don't know that there's three. But here, this is simply an object which is being dragged to the right with a certain force. So in these, and of course this is chapter 15, so everything is going to be done slightly different than energy methods because it's not energy methods anymore. It is essentially momentum. Sum of the forces equal dmv dt, and essentially you're doing a free body diagram, so to speak, integrating between state 1, T1 to T2, and mv at T1, mv at T2, dmv. So in the block case, for example, you're going to have to figure out the frictional force, the pulling force, and since you're doing this in the x direction, and since these basically do not change over, hang on, wait, get rid of them. Okay, since they change, whoops, okay, so there's your friction forces. Since they change over time, but they change in a stepwise manner, here, this is not exactly what we have, but say you had something like this. So this is T1, T2, T3, and T4. If, say, you were interested in the velocity at this point, and you had that your velocity at T1 equals to 0, you would simply integrate between T1 and T4 of the area. This is kind of a strange way of doing it. The area between or under this curve here. or that's not a good notation. So it would be the sum of the forces, or just in the x direction, dt, which is essentially, there's a better way of doing it, the area under this whole thing is equal to mv at t4 minus mv at t1. If we started at rest, your velocity would come out of all of the previous integration up to that particular time. So it's just nothing more than integration. Just so happened that the curve itself, or the equation or the plot itself, is easy to integrate. It's just essentially the area under here. Okay, if you go to the next problem, I think I may have. Okay, this is a similar problem in that what you really need to do is you need to do a free body diagram of all these terms and work them out together. He's essentially asking you, how fast is block B moving after 5 seconds? And block B is this one. You need to put everything together in here. And you have to, what I mean by that is here, like this. However, I should make a note that I didn't make a note in there that the mass of these pulleys and the ropes are all 0. Okay, let's see. Okay, this is a simple impact. Now let's see. I think the last one, I think there's one after this. Yes, this is in the video that follows the air hockey. This is a case in which A hits B, and it does have rotation, but I'm going to assume it's slipping over the surface. It's probably better that I should have done it differently and not put rotation in here. But as a matter of fact, I may pause the video and readjust this one. All right. I went in and corrected the problems here. This one is like a ball moving, not rolling, but like a bullet going to hit B. And I went in and stated here that I should have done before, the pulleys have no mass. So let me address this one a little bit, because this could be solved a couple of ways, and I'm going to sort of talk to you about it. But here's the deal. If you get down on a page here, let's see. If you look at this on a free body diagram, you'll have a normal force here, a weight here, frictional force, and a tension. Whoops. Now, you'll have a tension here, force due to friction, normal force, and a weight. Over here in this other one, you are going to have, it's 30 pounds, 0.5, 100, so on and so forth. But you've got 100 pounds over here. Okay, so the weight's 30, normal force is 30, frictional force is 15, tension's equal to tension. It's going to come up and over around this, and what you're going to have is 2T up here. I believe it's 100 pounds, but let me go back and check. Yeah, it's 100 pounds. Wait a minute. Yes, it's 100 pounds. So your first inclination would be you could, and it's okay if you want to do this as a check, sum of the forces equal mass times acceleration, find the accelerations, or you could sorry about that, I got distracted by my phone, which connected to a camera. Okay, so where was I? Oh, okay, so if this occurred over 5 seconds, occurred over 5 seconds, then you could look at this. If this occurred over 5 seconds, so did that. So you could essentially say sum of the forces in the X integrated from 0 to 5 seconds. During that 5 seconds, you let loose of this. The tension is going to remain constant through there. So what you would do is do this over that time. You would have, if it was released from rest, which it was, then you would have M V final. And what you'll have on the left-hand side would be making this positive. You would have T minus 15 is equal to the mass times the velocity of A final. Over here, you're going to have, you're making this plot positive, when in fact, if you're measuring your distances, this will be SA. Best thing is to make this SB, which means, now what you have to be very careful here, SB plus SA. You have to be careful about this distance because this distance remains fixed. So all this in red is the deltas to the length of A. This will give you the relationship between the velocity here and the velocity here. Once you have those, you'll notice you could do this same integration from 0 to 5 here. Sum of the forces in the y, say, where this is my y, equals to mass of whatever that is, which I guess would be B, and this would be A, B final. Taking care of the free body diagram, what you end up with is you end up with a T in here and a T in here. But you end up with a VA final here, and you end up with a VB final here. However, this velocity is related to that velocity, through the rope. And you can work the rest of the way out. So I think that's a good enough hint for that. And let's look at, let's see, that one. This one shouldn't be too terrible. And I could probably just do it right on this screen. Here. Well, the first thing you'd have to realize is this distance, this h, the minute after impact, you'll have a velocity of b, correct? Just the instant after impact. So after impact, if you do this, where this h is sitting right here, all your kinetic energy immediately after impact was converted to potential, and the measurement of h is a measurement of that potential energy. Immediately before impact, you'll notice it's not doing anything. However, initially this thing is coming at it at 10 feet per second. Now it's no longer rolling. It is a bullet, if you will, a very slow bullet. And there is no gravity. I mean, the gravity's here, but going down, but it's not making this go like that. It's, you know, this, in other words, here. The velocity initial here is like this. Just before they hit, this velocity is 10 feet per second. Now I've shown it over here, but what I'm implying is the instant they hit, it's going like this and like that, directly in this to that, in that direction. Now, if you want to consider, yes, parabolic motion, then think of it like this. Here's what's happening with A. Shoots in the parabolic motion, and it hits right here at the apex or the top of the height. If their B wasn't there, it would go on down. So in other words, you know, VAX is equal to 10, you know, VAY will equal to something such that right at the apex, then only velocity left is 10 feet per second. What is this? It doesn't matter, and how far it's shot back, it doesn't matter. You just launch this ball, it hit right here. And that is exactly the velocity prior to, or the instant right before impact. The question is what happens after that? You know, A, we don't care what happens to the velocity after that. What we do want to see is we want to see if, in fact, the coefficient of restitution is 0, what was that value? I'm basically getting you to explore what happens to the energy at this point. One thing you might want to consider is this. Okay, think about this. The energy, and I should have asked this question, the energy of this entire system just before impact is 1/2 ma va squared. Now, the mass of A, or the weight of A is this. So if you calculate the energy of this system immediately before impact, what would be interesting is figuring out the energy after impact. In other words, what is the energy of A immediately after impact? What was the velocity of A after the impact? Because the initial energy right before impact was only this. There's no energy here. And if I had to do this over again, I would ask you that question, but be interesting to see what you come up with. Okay, the last problem is addressed on a video by itself. And so I think this is pretty much it.